Hi, here to talk about the role of 2110 in future creative productions. My name is Chris Murray. If you don't know, I'm founder of Seismic. Spent the last 6 years as the CTO of Lux Machina, and before that, I spent about a decade doing consulting and contracting for Disney, doing interesting live entertainment productions, projecting on water, and developing systems for that, project mapping on castles and that sort of thing. And before that, I spent a good while doing high-end concert touring, theater, things like Blue Man Group and that sort of thing, generally weird stuff. Is what I've sort of littered my career with. What is 2110? I just want to sort of start this off as like a quick overview. I'm sure most of you actually know generally what this is. It's kind of been a bit of a buzzword for a bit, but generally it's a family or a family of standards that are describing IP video in a professional IP video. It's meant to be a successor to SDI and incorporates many other standards. There's 40 or something standards that sort of embody 2110. It also has tangential ones that SMPTE 2059, which govern timing. So the utilization of PTP and the SMPTE profile for governing how frames are rendered when. And the analogy to timecode that it also represents is sort of related. So why are we talking about this? Epic Games recently implemented 2110 via RiverMax. Epic has been basically working on this for a year and sort of tirelessly. There's a very small team of people that have been kind of putting this together and getting it underway. We've been testing it with them for a good chunk of that year. And it's come a long way, and it's much of it is available for release already and has been in since 5.2 and 5.3. Brings a lot more functionality. Yeah, anyway, so there's a lot of other competing standards that are currently on the market, like IPMX, SDVOE, HD, base T, NDI, et cetera. There's a whole family of them. They're all sort of part or pieces of the transition to IP, and they're all competing for various bits of it. Some of them are trying to aim towards flexibility. Some of them are looking for ease of use. Some of them are highest quality. Some of them are looking at minimizing bandwidth. But they're all kind of playing a different part, and people are using them for different reasons. In many cases, people are considering it a replacement for various types of cable. So we have people that are looking at utilizing 2110 or other similar protocols for replacing HDMI cable or SDI cable or DisplayPort or one of the various cables, or they're just trying to unify all into one, which I think is generally kind of a silly way to think about this, because I think it actually represents a pretty interesting shift in what we can be doing with technology once we start to actually work towards it collectively. And so what are some of the promises of the shift towards IP? Obviously, all these things. It sounds like the latest and greatest. It's going to solve all your problems. And I think, honestly, most of these are true in some way, shape, or form, at least eventually. I think right now we're still early days in a lot of this, so I think we should be careful of people walking away from this or generally in the industry thinking that this is going to solve all of their problems, because there's still a lot of work to do. Broadcast is definitely the same with AV. Fully embraced this. A lot of the existing implementations of 2110 are heavily leveraging hardware, and it's basically taking portions of what was SDI infrastructure and tacking on new connectors and processing at the very tail end of it, and it's kind of a 1-1 replacement for SDI. Implementations are often very static, and they're replicating standard frame rates, standard frame sizes, so like UHD or HD and things like that. And in many cases, people are just generally thinking about it as a replacement for cable. A vast majority of the implementation is not actually leveraging the entirety of what's possible. They're actually looking at what SDI is currently doing today, which is 10-bit YUV422 is the most common thing, and that's generally where a lot of the the I/O cards and stuff are actually implementing. Many of the decisions for what's actually existing in the market or what's about to exist in the market is predicated on leveraging existing networks and also leveraging a push to the cloud, because broadcast is absolutely looking at that as a way to ease deployment. If they don't necessarily have to move all this equipment around from show to show, it looks pretty promising to them, but that means that they need to focus on latency and bandwidth concerns. And so for that space, broadcast especially, they're leaning into things like JPEG XS, which is a very interesting compression technology, but I think it's not high quality enough for what people need in the virtual production space or even what people need in the live events and immersive spaces. It's not really meant for that. It's focused on, what happens in a broadcast feed typically, which is usually, talking head sort of stuff, and sports and stuff like that. And so there's like different needs that are pushing and pulling on that sort of adoption. But I think generally virtual production and live events, immersive, and people that are in weird, interesting spaces should not be leaning into that, and they should be leaning towards what else the spec is capable of, but it means that we need to start looking at what the implementations are like. And so, like I was saying, I/O cards and conversion hardware from like AJA and Blackmagic and stuff like that, they're generally leveraging what SDI is capable of, and they're tacking a thing at the end that allows them to transit traditional networks and utilizing DACs and fiber optics and stuff like that to get onto hardware, and then NMOS controllers that route the signals around and stuff like that, which I think is all well and good, but I think it is missing a little bit, and I think that's where NVIDIA and Mellanox have sort of excelled, is they've listened to us early on for the last 3-ish years about what's important to us from functionality and feature set as we transition to IP, and they've really listened to us for things like unbounded frame size, not putting any constraints on refresh rates. Really, the only constraint for us is bandwidth, and then occasionally we're finding edge cases in how they're internally processing on the card, because we don't necessarily have the same guardrails, right? Like if we can do any refresh rate at any frame size, we're bound to find some weird glitch in how the information's encoded onto the wire. And we do sometimes still, but it's getting better over time, but I do think it's the direction that this should all be moving in. And so outside of there being a cable replacement and generally how people are thinking about it, I keep thinking of the transition to IP as more of a hardware to software and less about trying to maintain what we've been doing, which is develop highly specific devices that do a very specific function or very specific task that cannot be repurposed. And if it doesn't necessarily have functionality that solves a current problem, it basically sits on the shelf and then becomes deprecated eventually when people are tired of depreciating that asset. And I think as we shift more towards software and we actually connect the software to layer together more directly through things like 2110 or other IP standards, I don't think 2110 is going to be the thing forever, but I think what's more important is the transition to IP. And I think leaning into high performance networks and actually leveraging the costs that we have been spending on things like KVMs and HDMI routers and SDI routers and all the infrastructure that comes along with all of those pieces can actually roll into the cost of actually paying for really high performance networks that have high bandwidth and deep buffers that can actually process these signals at an alarming scale that I think generally people aren't thinking about. And so I just want to kind of give at least some backstory to kind of like what the scale of some of these systems can be. And this should unfortunately say systems of yesterday. But this was a system that was put into Warner Brothers Leavesden Stage V to support House of the Dragon Season 1 and Barbie and a few other productions. But it's basically 14 racks of equipment that all is generally interesting bespoke hardware providing specific functionality filled with FPGAs. super capable, but very static and rigid and doesn't necessarily have great flexibility. You need to have seriously highly skilled staff to operate systems at this scale, be able to cater to like what productions need to do at any given moment, and so it's difficult. Nicole here for scale. Yeah, so here's a kind of smattering of some of the pieces of equipment that went into something like Leavesden. And this is from many different suppliers that we have to negotiate and figure out and track all their lead times and amass them all together and check all the functionality and kind of make sure it's all working and like get it going and make that all happen. Requires a lot of skill, lots of organization, generally difficult to maintain systems that are at that scale. And I think this is where we could eventually get to, where most of our conversion actually happens at the edge through things like the Matrox Connect IP. Having a master clock that generally is providing timing information in the system, and then everything else lives on the network. Obviously, this is missing like the compute. That doesn't necessarily change, like the only components in the compute changes. But like all of the terminal and infrastructure equipment that would go around supporting the massive infrastructure that supports these big stages, or even stages that get popped up to do a one-off production for the course of a couple of weeks, like they all still share a lot of the same infrastructure. And I think if we embrace sort of shifting towards IP and software, that we can actually reduce a lot of the complexity of the system, but it means that we need to embrace software in a pretty big way. And so that was, trying to go over the systems, at least somewhat at scale, but I want to also talk about some of the methodologies and how we sort of arrived here. And this is actually one of the first times that we did a dual frustum on a volume. This is in 427 at the Nance stage. I want to say in early 2021, but honestly, I don't remember anymore. But we have imagery that's all on the walls and the ceiling that's part of the outer frustum, as I'm sure most of you are aware. And then the spaces that are outlined in blue are the two inner frustums that are being rendered simultaneously and tracking the two cameras that exist in a particular position, left and right. And I want to kind of talk about how we were utilizing multi-GPU to kind of balance the load of all those things and what that looks like as we transition to IP and away from each individual system being responsible for rendering the entirety of the load. And so this is sort of a close-up look of one specific node, super basic, 2 GPUs, NVLink. GPU 2 is responsible for rendering at least one frustum. We have to make decisions about where the second frustum gets rendered. Either it's shared both on GPU 2, or we're assigning it also to GPU 1, and we're reducing the resolution of the other viewports in order to balance that load. And that first GPU then drives the display. And this is sort of happening across the entirety of the cluster, but I'll get into that some in a bit. But this is sort of a very small look at what the methodology is changing to, or what I think we should be changing to. In this case, we have 2 nodes that are sort of demonstrating this. All of the GPUs in node 1 are responsible for rendering the inner frustum, right? And so we could have both of those inner frustums rendered on a particular GPU on a specific system. We don't necessarily have to figure out where we balance the load. The compositing and the outer frustum rendering happens on node 2 in the sort of typical traditional sense, except for this time, instead of exiting the GPU like it normally would, it actually is exiting the network card. In this case, let's call it Mellanox or something like that. That would then drive the GPUs directly over the network, or sorry, drive the display technology directly over the network. And it doesn't really look like there's any real savings here at like a very small scale, but it will look that way once we kind of scale this up to the size of some of the largest volumes that exist. Forgot about this slide, sorry. This is an interim step that I think most people are actually going to be getting to in the near future, just because capital expenditure is tight right now. A lot of systems that have been put into production, you don't want to necessarily throw the baby out with the bathwater, trying to revitalize some of these systems. So in this case, we'd actually do what I just described, but instead of transiting the network card and driving all new network hardware and having a super robust network switch, you can get by with having a smaller network switch and still transiting the GPU to drive the traditional display processors in that way. But getting back to the render nodes at scale, this is the sort of traditional model where I've got 12 nodes here, and sorry, this could be better, but this is sort of one node here, this is another, and so we've got 12 that are driving 24 displays in this case. 2 outputs out of each machine. Every single one of those GPU2s is going to be responsible for rendering an inner frustum, and then that second inner frustum, if we go back to like the visual, we would need to decide where that lives. Either it's sharing a load with GPU2, or we're playing tricks with scaling down the outers in order to make room for that second frustum to be rendered somewhere on the system. And I'm really sorry for this complication. I'll try and explain this, but it was the only way that I could smash it all on one slide. But in this chunk here, I'm basically calling this like a bank of inner frustum renders. These are all of the outer frustum renders and the compositing that would be required for driving all those same displays, because we are taking the load off of rendering those inner frustums to specific machines that will then go over the network, hit the switch. They'll be multicasted from the switch to all of the renders. The renders then will have twice the amount of available compute. They can render twice as many outputs as they previously were. And so we basically reduced the size of that system that would actually be needed to drive that. And so we could just say, well, we only need this one machine to render those 2 frustums. And now we've basically got 5 machines of savings that didn't need to go in that system. Or we could potentially leverage those machines for doing something else. And I think what will be interesting is when we actually get to the point, and software is matured enough to where this can all be orchestrated from a high level, and we can decide how any of the components of these systems are actually leveraged in any given moment in time for the active production. So if we need more compute because we're running into a performance issue and it's, man, we really need some extra horsepower over here, I think we'll get to the point where we'll actually just be able to provide that. And so the way that I think that will happen is through subdividing the actual inner frustums, where we have multiple GPUs that are simultaneously rendering a single frame. This has some caveats currently. Obviously, screen space effects and things like motion blur and stuff like that will be hard to manage in this case. You'll have to have things like overscan, or we'll need to fast forward to the point that we're actually ray tracing these things, ray tracing and path tracing these things in real time, to where we're no longer concerned about those screen space effects, because those will be able to transit the edges of machines pretty reasonably. But it's going to take some time. Like, this is not a tomorrow problem. It's not even a today capability. Like, this is something I think we should be working towards. Where we're at today is basically delegating a specific GPU to a viewport that would transit the network, and it would work in the same way that it has been, except for we now have increased efficiency because we can move that onto a single machine, multicast that over the network switch, and get that to all the render nodes and basically double their horsepower if they've got multiple GPUs, or if they've got 2 GPUs. I think it's also possible, and we've done some early tests, scaling this up to 4 GPUs per machine, and that does function, but you have to be careful about the load, because obviously you're processing, you need to start moving to like dual processors and 128 and 256 cores in order to leverage that many GPUs simultaneously, because Unreal does have a lot of CPU side requirements for actually making all of this stuff run in real time. But there are some other advantages that isn't necessarily just like virtual productions. I think simulcam and AR workflows will be greatly improved. In latency, I didn't mention it before, but latency, even in the previous cases, is significantly improved and dramatically improved once we start talking about like real-time compositing for simulcam and things like AR graphics for broadcast shows and stuff like that. And so I'll show like kind of what it is today, where we have an SDIO board that's interfacing to a camera and local monitoring if the operator wants to be able to see the composited images so that they can actually frame up whatever digital character or graphics might show up on the digital feed that they wouldn't necessarily have access to. We generally think that's important. But in most cases, we actually transit the textures from SDI through the CPU system memory and then to the GPU, which actually adds massive amounts of latency. It makes it feel really, slippy and stuff like that when we're actually doing simulcam and stuff like that. And like, there's ways around that, but it only happens by adding increased latency. So in this case, like, we want to reduce latency. And so there are certain I/O boards that do support DMA, where none of those textures will actually bypass the CPU system memory, and they'll only just transit back and forth between the GPU. But that's not always common. And I do think like this sort of step that happens here is probably going to be our uphill both ways in the snow in terms of like visual compute, because moving forward, like, all of this is going to live on the PCI bus and never occupy CPU space anymore. And I think that will actually help with physics and other things that we need to happen on the CPU side, basically just raise the bar of what's available there. But this is where we're headed towards, and honestly, some of this stuff we're capable of doing now. In this case, we have a Mellanox card connected to a GPU. DMA textures are happening directly back and forth. Camera is spitting out 2110. That's transiting the system. And then we also have a return feed because it is a bidirectional link. Now that we're on a network, we can actually utilize the unused bandwidth to actually send the composited feed back to the camera so that the local operator actually sees all of the digital content that's being composited on the feed to allow them to actually frame up shots and have good visibility without adding an additional monitor. It's basically a button that they can press on the camera and actually flick back and forth between them to see the digital versus the real. And Red has already got this going. Like, we've seen this happening. So, and that happens via Red Connect, but like, I do think that this is the way, in my opinion. And so I just kind of want to talk about some of the other aspects of like the production technology and how that's changing for them as well, because it's not just on the Unreal side and the rendering side. On the camera side, again, the broadcast and AV markets, they've been adopting 2110 cameras for a long time, and like, not a long time, a few years, but I think it's in a different class. Cinema cameras, I think, are doing a very different thing. It's a harder problem for them. But Red has a fully synchronized via PTP, supports 2110 and other IP capabilities like R3D over IP via Red Connect. And we can actually work at arbitrary frame rates on that body. If you want to shoot at 56 or 92 or 71, it's possible. Like, we can do that there with synchronization and PTP. So whenever a DP or cinematographer is asking for us to do something specific for creative intent, like, we can actually do that. Right now, it's technically possible, but practically impossible in order for us to do that. EID is a nightmare to manage, and like, these systems are at such a scale that it would just take hours for us to flip that over for a shot or two, and it just doesn't make any sense. ARRI has also demonstrated the ability to do PTP synchronization of their cameras at project rates. They've said that it can work at arbitrary rates, but I think we're still, I don't know if it's months or days. I'm not part of their team, but I think it's going to be a few months at least, if I'm guessing, of when that might actually come to pass. But I also think the transition to IPs can greatly streamline the production behind the camera and that whole process into editorial. Like, right now, we have cameras that record to mag, goes through ACs, film loaders, ends up in editorial. It's cards that are basically being swapped back and forth constantly. Constantly trying to manage, the time that's remaining on the card and gamble whether or not you can fit the next take in it, which, often leads to 5 minutes of downtime every so often. I think we can actually bypass once these cameras are actually directly connected to the network. We have centralized storage that all of the available cameras that are on that system that are shooting in production, basically their frames will just be recorded straight in a disk at the DIT or something like that. They can QC frames while they're happening. So things that are difficult today, like frame-by-frame playback off of a body, some cameras have it, some don't. we can just do that by constantly inspecting the footage that's rendered. We don't have to go to the mag, pull it off, go through a whole process to get that into something that somebody can go through. And so inspecting for things like moire or image artifacts or stuff like that, I think in the future, once we sort of embrace this switch, it'll be a lot easier for us to make decisions about what's happening, whether or not something is or isn't working, because there's so many places for it to go wrong with all the downsampling that happens on monitors. It's really difficult for us to assess what's actually happening in the frame. So I do think that's something that's going to provide a lot of benefit for us down the road. I think one other benefit of having a bidirectional link here is that as we move forward, we're going to have the ability to inject metadata onto the body, and we just need to decide whether or not that's something we want to have happen. In my opinion, it's something we should absolutely work towards. Getting things like the camera position and orientation directly into the metadata of the frame is huge. If that can transit all the way into post without a weird process of who's going to put what where, and it all get annotated in emails, and everybody making sure that they dotted their I's and crossed their T's about where the data exists, like it's a nightmare. Like if you've been in production trying to get mocap data from point A to point B or camera tracking data from point A to point B is really difficult. And so I think the more of, like obviously mocap is an exception. I don't want to put skeletal animation into frame data, but like there's no reason that we can't be putting the camera's position and orientation into that data, or even something like, let's say you were on a shoot that had a gimbal. The gimbal's orientation and position could be put into the metadata of that frame, so when visual effects gets that data, they can just work on it without having to worry about how are they going to get the data from, you know, the service provider and figure out how to or morph that data from whatever format it existed in into their own pipeline. If this is something that can exist in metadata that we can agree on, like this is something I think we can all move forward with, and everybody I think would benefit from it. Yeah, I think also there's having a centralized control of cameras and camera rigs for things like plate shoots where we have these massive arrays of cameras. Right now we end up with multiple lens control systems where it goes to an array of, you know, Prestons or REs or whatever that for adjusting the LCS, where if we can unify those things, we can actually treat these things more of like one organic unit, especially in the cases where we're talking about arrays of cameras where we're not making mistakes where one of them gets bumped or the wrong focus position gets set on one of them and screws up the stitch for the entire thing. Like I think as we move towards that, it will be a big improvement. And I do think there's other places like lighting specifically, I think they're kind of furthest behind this gap in many cases. Lighting protocols today don't really enforce frame rates really. There are standards like streaming ACN that allow for arbitrary rates, but at the end of the day, it's up to the fixture and their own internal timing, or in the lighting desk, its own internal timing. Like some desks still work at 29 FPS or 25 FPS. Or 40 FPS or 44 FPS, and then you have fixtures on the other side that may be working at 44 FPS, and it's really hard to get really specifically timed control of lighting fixtures today without getting into really interesting setups or home-growing your own solution where you're taking industrial lighting and building your own controllers around them and bypassing what's happening in the entertainment lighting, you know, market or space. And so Kino Flow is probably the furthest along. They've actually embraced Megapixel, which has basically given them capability of 2110 accidentally. But that processor can work at arbitrary rates. We can drive that fixture at arbitrary rates. Like this sort of folds into the system, and it's the furthest along. Cream Source is, I would consider, is probably somebody who's next. They're doing this through distributed sync pulse that you can generate yourself, and so we've done some tests where we basically have that run at arbitrary rates, and it does work, but it's complicated for production to set up. I'd rather, in the case of traditional lighting, that it actually just incorporates things like PTP so that we can get accurate frame data out of the lights from the controllers onto the subjects and timed with video or with the rest of the visuals so that the frame feels cohesive and compelling. Yeah, and so why is it important for all the synchronization to happen sounds like it's, a future problem and like it's only something that people are going to be facing in the future. But the reality is like people have been facing this for years, especially in the research space. This is a small volume that exists in Pittsburgh at Meta Reality Labs called Mugsy. It's about 170 cameras that are all timed, synchronized, and looking at a particular subject and trying to pull various pieces of information for everything that they're trying to learn about people and stuff. But there's tons of lighting that are incorporated in this. They've built their own controller and stuff like that in order to synchronize these things because the current lighting market doesn't support this type of endeavor. And as we increase the amount of things like bullet time that exists or nerfs or Gaussian splats or whatever the next waves of things are, generic volumetric capture, that all gets easier the more that we can finitely time these systems and tune them and make them reliable and actually run. Because like right now is very difficult, even in the volumetric capture space that's a bit more mature. It's lots of data, goes to very bespoke places and very bespoke processes, and I think we can get this to a place where this is a lot easier to do, even on a film lot, where people are having to scan assets and scan people on the side of a stage because it's the space that the production has available. So I think the more that we get down this path, the easier that it's going to be in that transition. And live events is not honestly dissimilar from a lot of these other things. Many productions are still suffering, literally to this day, with EDID. Like, productions are failing to this day because of things like EDID. Switching to 2110 doesn't necessarily negate that. SDP is a pain in the ass at the moment. If any of you are familiar, it's a text file that's almost human readable, but it's at least monumentally more readable than 128 bytes, or 128 byte message that you need to unpack that is EDID, and trying to figure out how all the different GPUs read EDID and decide what they want to do with that information is pain. It's a painstaking process that not very many groups on this planet know how to make that function. Live events also needs unbounded frame sizes. Things like Coachella have these really long, wide, expansive LED stages that they would benefit from being able to have those at whatever resolution and whatever frame rate that they felt best fit. But in this case today, it's always broken into chunks of broadcast standards because it's easier to monitor and it's easy to distribute. But I think in the future, a lot of that will go away and we'll simplify some. They also have really complicated setups that they have to set up very quickly. In many cases, live events and concert touring, they only have hours to get some of the most complicated systems up. Things like Coachella, they've got 4 or 5 days for something the scale of Coachella to get that thing together, and they need flexibility and the ability to maneuver signals around these systems. You have also bands that come in with band ads, and you have basically a dozen, if not more, systems on top of the main system that all need to work together. And I think if we get this place, or if we get it to an IP place, it's a lot easier to connect all those things together in a sensible way. And things like IMAG absolutely require low latency, and moving to IP will definitely shave that off for them as well. But I think what's important here is to actually show that it isn't necessarily the broadcast space that should entirely be dictating what the technology and the software that we're putting forward. I think there's enough commonality between what live events, what virtual production, and what research and development needs, that there's actually commonality here that we should all be moving in that similar direction. So what's the catch? Because there always is. Today, the control systems for any of this stuff just doesn't really exist. There's people that are building it. I would consider myself one of them, but it's still like early days. Epic has some implementation that allow for generating these signals, but how they all piece together into a cohesive system that operators can sit in front of and at the push of a button get data from point A to point B is still yet to be seen. Like there's some work for us to be collectively doing there. And the workflow is not completely understood in terms of how do we want to control all these systems, how do we want data to be coming off of these servers, how many streams of 2110 do we want? Is the desktop a stream of 2110? Are the outputs that are driving the processors different streams? Are they concatenated into one stream. What does a KVM system that look like when it's entirely in software? Like, we don't know what that looks like today. I mean, I think I know, but I think generally there is not necessarily product for solving these problems today. Swap buffer synchronization, so this is like swap groups and the ability to keep multiple outputs in sync that we've been utilizing with NVIDIA via QuadroSync, or even AMD via the S400 in yesteryear. All of that happens, that synchronization that keeps the different outputs from tearing next to each other, all happens in a hardware layer that's not directly accessible from software. So one thing that we've lost in this switch to 2110 is we no longer have the ability to daisy chain a few S400s together and keep all those outputs in sync. So what's happened today is that's actually moved to a software layer that Epic has developed. They built a profile or a protocol that's proprietary to them. I mean, like, it's open, anybody can go look at it. That allows for the synchronization or the frame gating of these signals. But in my opinion, when it happens in the software layer, unfortunately, when the system is under extreme load or duress, it's really difficult to actually synchronize and gate that information because you don't have enough cycles to actually appropriately know what's happening on the system. And we've seen this before. Prior in 426, there were some experimental features that we were testing out that was doing specifically this. And it did have these caveats. Basically, if we were running and we ever hit a spike that was greater than 50%, we'd end up having to bring the cluster down and back up again because the simulation would be out of sync with itself and there'd be no way of making that work back together again. So what I'd like is for all that to move to hardware, and we actually put it on the display processors and the display manufacturers to understand frame gating and communicate amongst themselves over their IP networks when they should or shouldn't switch. And they're already doing some pretty complicated tasks for the automated backups for LEDs, where they basically feed tiles from the top and the bottom in order if a processor fails, it automatically picks up on the second one. So like, they already have communication between these things. So I think it's possible to do. Component lead times are still totally crap. When we're talking about networking hardware that is in the scale of what I'm talking about, where it is really high port count, really high performance, 100 gig, 400 gig, 800 gig type frames, the market is still gobbling those up. It's really hard to get the FPGAs for that. And in some cases, some of the hardware is over a year to actually acquire. NVIDIA also is it's a little bit of a crapshoot for the specific hardware that you need to run under Windows, the Bluefield range. You might be able to get one model one day, and then you might have to wait 6 months for that same model, so you may be forced to switch to another version that maybe doesn't have a specific functionality that you were relying on, but maybe not. And so those are things you have to think about when you're designing these systems or you're trying to amass inventory for tackling whatever your productions are going to be. And at least in the short term, the teams to build these systems and decide how this workflow works are going to be highly skilled workers, and it's going to be difficult to find a lot of these people that actually understand what needs to happen and how to build the infrastructure around it, because it's not just add it to the Unreal Engine and you're done. There's a whole ecosystem outside of this that needs to exist in order to make production successful, in my opinion. And so these are some things. It's the last slide, I promise. These are some things that I think it's important for us to not lose sight on. Synchronization at arbitrary rates is important to get to a global project rate. And in my mind, I've been thinking about this as we have a dial that sits on stage that governs the frame rate that everything is running at. And when we go to 120 or 72 or some other frame rate, it should be as easy as switching to that frame rate, and the cameras move, the renderers move, the lights move, the lighting consoles move. And from that point forward, all of the effects and everything that's being programmed can at least happen in the same data frame. And I think that's actually really important. I've got an anecdote, at least from some work we did on House of the Dragon, trying to synchronize lightning flashes between imagery that was happening on the LED walls that was meant to be captured in camera and lighting that was mapping onto subjects. And we needed those things to look and feel like it was happening in the same space. And it was really difficult for us to make that happen because we were running at 44 hertz to the lighting fixtures, and there was no way for us to get around that. Lighting console's effects were working at 30 hertz and it was not compatible with 24. And those things end up turning into little esoteric timing problems that are not repeatable. And so you may get it on one take and not the next. And so what we end up doing is catering the visual effect in a way that makes it more reliable, but isn't necessarily what the creative intent was. And my hope is if we can get to a place where these can all be finitely timed, we won't have those problems anymore, at least not in the same way. Unbounded frame sizes will allow for greater flexibility if we can arbitrarily resize any of these frames, and if monitors can look at them. Right now, most monitoring that exists is looking specifically at broadcast sizes and broadcast rates. We can't just plug in arbitrary NVIDIA-generated 2110 stream into a 2110 monitor. In most cases, you get a totally broken buffer. Most of them are not fixated on generating 16-bit floating point textures that 2110 does support, and we've been utilizing with Unreal Engine in order to pass effectively the rendered back buffer around the network without any real material loss. Being able to QC those signals on a monitor is not something you can do today. I am not aware of a monitor on the market that supports decoding of a 16-bit floating point image, but we can do that in software, and very easily. And I think there will be many unforeseen advantages of connecting all this software together, where we have people with very interesting ideas that the only thing that's keeping them from testing and executing them is the time and ability, and it not necessarily being the hardware doesn't support that. And I think if we get this to a place where the only thing that is binding us is the bandwidth, we can decide whatever it is we want to do with smashing data down these links and connecting these render engines together to do really interesting things. That's all I got. So thank you.